Hello folks, I'm Dave. I'm a specialist solutions architect at AWS covering security and compliance across Europe, Middle East and Africa, but security geek is kind of more succinct. I've been at AWS for just over 2 years now and been doing security for a couple of decades and a bit longer than that.
And my name's James Brown. I'm the VP of Technology Solutions at Alert Logic, ex-AWS, and work very closely still with the guys at AWS.
So what we've got for you today is a quick introduction to what we consider serverless architectures to be, a little piece about threat modeling and how we go about looking at threats from the point of view of serverless particularly, just a piece about easy wins on access and permissions constraint, and then we get into the really fun new stuff. So James is going to talk a bit on some work he's been doing about wrapping Lambda functions to do API filtering. I'll be following up with a piece on actually using API gateway in place of API service endpoints, which is a piece of work that I then figured out could be generalized. And then after just wrapping that up, there's some interesting research that I'd like to give you a sneak peek of afterwards. So starting off with what serverless architectures are all about. Everyone's been going on about serverless architectures in the last couple of years, especially since we released Lambda. But to be perfectly honest, they're a long way from new. I mean, S3 is essentially serverless in and of its nature, and hey, that's been around for 10 years now. So if you're familiar with the shared responsibility model that we have, please raise your hand if you are. Great, that's a large number. If you haven't come across it yet, then please take a look at things like the AWS Risk and Compliance white paper or the AWS Security Best Practices white paper that give you a nice diagram of how the services in AWS stratify from hypervisor up to your application and data, and where responsibility demarcations are in that. Or indeed, there's a few videos on YouTube of some of us, including me, doing presentations on how they go in more detail on how this fits across our different infrastructure and container and abstract services. So serverless environments normally are abstract services in that you, the customer, don't get to have a server instance that's sitting there running Linux or whatever that you can SSH into and control directly. You wind up dealing with it through an API or through some other kind of interface. And we look after all the underlying stuff so that you don't have to. So the idea about serverless is that you guys just need to worry about the business functionality and purpose that you're going to be turning the service to, and we look after what people who want to deal with things at that level would consider the dull stuff. So it's also been suggested I just touch on what serverless isn't. So if you can SSH into it, it's not serverless, although you could potentially do something whereby you could do that with a Lambda function, but it would be horrible. And yeah, essentially we look after it. Oops, hang on. Thank you. This slide was current until 6.5 hours ago. Pace of innovation and all that. And it's probably going to be even more out of date this time tomorrow. But the idea here is this is most of the services that we offer that I'd call serverless today. I had actually missed Trusted Advisor off of this, but as you can see, there's 40 of them. Now, in the much vaunted 70-something services that we talk about offering, this means that more than half of them are effectively serverless, which is an interesting point worth to note. The other thing, of course, that you get a lot in serverless architectures, and this is just a slide of a nice architecture I lifted from a reInvent presentation from last year, is you get a lot of API-level communication with external services as well. So here we've just got an IoT monitoring and chatbot service that's talking out via APIs to Twilio and Slack, and also using other things. So yeah, you've got Kibana and Elasticache and so forth going on in there. So looking at the world through security-tinted glasses as I do, I always start thinking, so here's an architecture, now what can go wrong with it? How could a bad guy break it? So this is where we get into threat modeling a bit. Now, as Bruce Schneier and other luminaries have accurately said over the years, the human brain is awfully bad at doing threat and risk analysis, fundamentally. And I think this is borne out by the fact there's a considerable number of frameworks actually designed for doing this precise thing. There's a MSc thesis I read a year or so ago by a Dutch chap named Dan Ionita from the University of Twente. And it serves as gazetteer, if you like, of threat and risk analysis standard methodologies. He came up with 27 of them. There were a couple in there that I hadn't heard of before, but there's a couple I knew about that he hadn't got in his paper. So we use a whole bunch of these things, Stride, Dread, others. There's an interesting paper worth looking out if you haven't seen it already. Every so often, some of our guys do actually get to publish papers in learned journals. And Chris Newcomb and others did a paper that turned up last year in the communications of the ACM on AWS's use of the TLA plus modeling language for doing formal modeling and analysis of our particular security critical bits of code. So this means that we actually kind of walk up to the line of doing formal proof in security critical aspects of our environments. So if you're doing threat modeling, you identify who the bad guys are, how the bad guys might get at your environment, probabilities of them doing nefarious things, and you do stuff to try and stop them. So looking at a generic AWS service, you've got potential attack vectors at application level and at API level. Ultimately, if it takes input, it's potentially an attack vector. So we've got application stuff, API stuff, and let's look at what the outcome also of a successful attack would look like. Disruption of the service is an obvious successful attack, reduction in responsiveness, your classic DDoS, but also think about if a service could be used rather than a compromise itself, being compromised itself, being a conduit of an attack to some other internal vulnerable system. So let's say, for example, if you were to put a message on an SQS queue that with some badness in it, in the anticipation of an EC2 instance that may have a vulnerability in it, consuming that message and being compromised as a result. And this is where you get into kind of an API level look at almost an equivalent of the OWASP top 10 in terms of cross-site scripting, SQL injection, all that stuff. So let's look at our API endpoints to begin with. And they're actually looking pretty reasonable. So they are large, they're scalable, but they're finite in size. From the point of view of confidentiality, integrity, and availability, we use HTTPS using S2N, so that gives us TLS 1.2. We scale them, so that's our confidentiality. We scale them, so we've got our availability. We also rate monitor them, and there's actually good reason why you want to have a separate development and test environment from your production environment, because if you write yourself a bug that causes you to start hammering on our API, we'll wind up throttling your ability from that account to go making API calls. We have signature v4, which gives us, by the fact that you're signing your API requests with your secret access key, that gives us strong integrity and strong non-repudiation. We're looking pretty reasonably set here. In-band is more interesting. So I just picked a selection of serverless services here. And obviously a bunch of these have means of triggering Lambda functions. And in terms of the kinds of messages and message sizes you can pass into them, some of them have the ability to take some pretty big messages and objects. So plenty enough scope here to go embedding badness in. So what are we going to do about this? First thing, easy win, ensure that only the good guys have the ability to get at your services. Start with IAM. We all know how to actually go using IAM and its conditions to constrain things based on source IP address, time of day, user details, obviously. and also limit the scope of what can be launched. So it's also worth ensuring, if you're not already doing this, we really like the idea of ensuring that service access, anything privileged really, can only happen from a role rather than a user or group. Reason being, if you're assuming a role in order to do anything interesting, then this brings our secure token service into play, which means that in order to get yourself into a context whereby you can do something interesting, you actually wind up using ephemeral credentials rather than persistent ones. So we've probably all met the software engineer who has hardwired credentials into a script and then gone and sent that script to somewhere like GitHub and suddenly found that his account is mining Bitcoin. If he's only able to use a role and the ephemeral credentials that it provides to actually do anything privileged, then that gives him no incentive to go hardwiring anything into his code and thereby closing the door on that particular method of compromise. Also, if you start actually using cross-account access and multi-account environments, and for this, there's a video that we did earlier in the year from the UK Security Roadshow, which talks a bit about a reference architecture we have for multi-account environments. Then you can actually get something close to mandatory access control, as well as limiting the scope of any issues that may arise in a given single account. In the context of cross-account and access and multi-account architectures, I also commend to you two other sessions here at reInvent, SAC310, which I believe was yesterday, and SAC320, which is coming up. So these are specifically on cross-account architectures. Recommend having a look at them. So IAM's your first port of call. Also, while it's still a large list, you can potentially do some limitation on your service access based on whether a call is coming in from an Amazon address or not. And we will actually be making reference and use of this JSON document later. Also, you have the means in IAM to review details of your roles and users and groups and see when specific permissions were last used. So if you've perhaps made a role slightly overly permissive, if a particular permission hasn't been triggered for a number of months, then chances are you're probably going to be able to drop it. So at this point, I will hand over to James to talk a bit about some alert logic work.
Thank you very much. Okay, so as I said, my name is James Brown, which I bet none of you thought you'd be seeing James Brown in Vegas, but you are, and apologies if that's the reason why you came here. So I work for Alert Logic. We've been securing AWS workloads for about 4 years now. And this whole piece, like all great things in life, really came up after having a conversation and a beer with David after one of the AWS events that was run last year. So all the attendees went into a room and they all got told about Internet of Things and serverless architectures and came out all very excited. And we had a couple of very, very large UK brand names come out and saying, okay, this is great. I can really see how this can help. It's going to help me get around scalability problems. But we've got security and compliance issues. So how are we going to run this in a secure way? How are we going to meet the compliance requirements that we have? And when you looked at the issues that they were facing, they really split into two buckets. One was, how do they effectively understand what's flowing into the system? How do they inspect the data that's flowing in? And secondly, how are they going to collect the logs from the operating systems running it? This, we're going to talk about how we can sort of examine the input and how we can sanitize that. The problem with the logs is a greater problem. I mean, if you have compliance that's telling you that you need OS logs, then you are going to struggle on serverless architectures. That may be forcing you back into an older route of doing things. So what we did is we fired up a research project. We'd like to understand, what's hitting our AWS customers, but also we want to understand really where our AWS customers are going. So this was a research project that we started up to try and understand, okay, how can we look to start to secure serverless workloads? So let's start with Lambda. Lambda's a great place to start. It's one of the most mature pieces of serverless infrastructure. It can kind of take input from anywhere. You can do a bunch of stuff with it, and then you can push the output pretty well anywhere you want. You've got a huge amount of control, and you don't have to worry about all the infrastructure that sits underneath it. What could possibly go wrong? You can write insecure code in any language that you pick. That's what can start to go wrong. Okay, so you're going to have this gloriously architected serverless architecture. It's going to pick things up, and then it's going to start running through the code that you're doing. And this is where problems can start. What you do have to remember with serverless architectures is just because you haven't necessarily got a website, just because you're not necessarily running on IIS or Apache, just because you've lost a lot of these things, does not mean that you can really start to sort of forget about the security pieces. As David said, you need to look at these, you need to understand how you're going to model threats, you're going to have to understand how people can possibly attack you. So, let's take security rule number 1, sanitize user input. So, yes, it's a very amusing picture of a car with a SQL injection attack taped to the front of it. However, think about it. You guys are all here because you like or want to do serverless architecture as you are. If you had to write a national system or statewide system, if you're in the US, for example, a toll road, or for example, speeding fines and so forth, isn't that just a perfect use case for serverless architectures? I'm going to take all these photos from all these different cameras, I'm going to throw them in an S3 bucket, I'm going to pull them out the S3 bucket, I'm going to process it, I'm going to do something with it, and then I'm going to check this with a backend system. It's a perfect use case for a serverless infrastructure. So that's really the kind of what we were starting to try and look at. How do we help in this kind of case? So if you take the world's simplest app, we're going to have an S3 bucket that all these cameras are throwing photos of cars into. There's going to be a Lambda function picking them out, doing some stuff, grabbing that license plate off it, and then it's going to be calling a back-end system. And as Dave said, the back-end system could well not be yours. If you think actually about this use case, the chances are that you're not going to have the system that has all the number plates and names and addresses. That's going to be a third-party system, most likely run by the government. And at that point, you may find it's a system that's never really been exposed to the internet. So how do you know this is secure? How do you know what's going on within this system? You're calling a third-party system that's outside of your control. You need to make sure you're sanitizing the input before you call that system. So this was the problem. How do we start doing this? So we decided the best way to secure serverless infrastructures was using serverless infrastructures. So what we did is we were looking at putting in a Lambda function before. So how can we separate out the code that sat in the Lambda function that your developers are writing into more of a sort of security proxy at the front of it. We've also got some pieces at the back end, which Dave is going to cover off after my piece. But really, we were looking at this front-end piece. So when we start looking at it, photo goes into the S3 bucket or data goes into the S3 bucket. It's going to trigger, an event within this security sort of AWS Lambda function, and that is going to pass that data to a security piece, whether that be code or whether it be a system. It's going to be something that can understand what good is and what bad is. That's going to go and pull out the data, it's going to analyze it, and if it looks okay, if it's happy, it's then going to invoke the original Lambda function that would have been the one picking it up. That can then go and get the data and can go and process it. So really this is trying to sort of separate out the functional code of what you're trying to do with really something up front that you can control that's there to sanitize that user input to make sure that you're not being attacked. So there's some considerations. There's synchronous, asynchronous. In the case of taking in license plate photos from cars, that's a classic asynchronous system. No cars waiting, in real time to be told they're speeding. Whereas, you also have synchronous. We're now seeing, serverless infrastructures pushing out web pages and taking input from web pages. For that, you're going to want to understand, things in real time. You've got things like machine learning or analytics. So quite often, if you've got a vast amount of data coming in, you may not be looking for anything that's specifically bad. You're just looking for something that's different to what you're normally getting. And there's things like malware. This is one point that we've had a conversation with a number of customers about. Maybe your customer base is uploading data. It could be photos. It could be CVs. It could be job postings. It could be, data. And at that point, you may be processing it, and you may well be passing that data out to other customers. Are you sure that someone is not maliciously pushing in malware within a document just to be handed out by you to another party for the malware to actually spread? You need to make sure that you're not effectively the vector that's spreading the problem. And then we're also looking at sort of, classic cross-site scripting SQL injection attacks. And we've mentioned SQL injection attacks a few times, and this is one of the things we get. Really? SQL injection? 2016? Is this still a thing? Yes, it is. This is not the most hideous wallpaper known to man. This is actually a graph of the attack types that we see. Did you like that? It was good, wasn't it? This is actually a graph of the attack types that we see. So we've got about 4,000 customers, and these are the attacks we're seeing coming over the network. And what's interesting, if you can see it, is really, if you look at it this year, we're actually seeing an increase in the amount of SQL injection attacks that we're finding. And in many cases, they're not necessarily attacking your code. Developers get very personal about, I used to be a developer, very personal about SQL injection. We're fine, we're using stored procedures, it's not going to be a problem. If you're running on frameworks like Magento or e-commerce platforms like Magento or frameworks like Django, in fact, you may find the SQL injection attack is not aimed at you, it's aimed at the framework that you're running on. So we see that a lot. If you take this example, this is a SQL injection attack, which I'm sure you can all see. This is one designed to attack a Magento server. So our research department fired this up, and you can see there, that is the SQL injection attack. It's just base 64 encoded. So that's really what it starts to look like. So don't underestimate SQL injection. So we decided to go and have a look at this in a little bit more detail within our research project. So what we did is we downloaded some code off the internet, because of course that's where we all develop nowadays. We downloaded some code, and really this code was there to hand out a web page out of an S3 bucket. So I've got no web server, it's just being pushed out of S3, which is really the world's largest web server. And at that point, the code is going to render, or the page is going to render for the user, they're going to type in their username and password, and that password is going to be submitted or posted into a Lambda function. Now again, for us, we put in this kind of security wrapper, this piece in front. So that's going to receive the data. That then is going to pass that down to our SQL injection analyzer. So we pulled it out of our system and basically hooked it up to the Lambda function. And if that passes it, if it's okay, then that wrapper is going to invoke the next function down, the original function. That function is then going to reach out to an RDS database, validate the hash of the password, make sure it's okay, and then go and get a token from Cognito. So really, we're looking at how we could, again, introduce this kind of function before the original code to try and validate this input. The Lambda wrapper is fairly trivial. All we're doing is we're taking the data, posting it out to a system, checking the response, and if the response is okay, moving it back on again. So as you can see, the research department do not do pretty websites, as you can see. This is basically their sample login page they were doing. Someone's put in a valid email address, they put in a valid password, they've clicked the login button, and they've logged in, and that's the Cognito tokens. You've got the GUID back from Cognito with the tokens. So that went in, that worked. That's valid traffic, we want to allow that in. On the flip side, and again, the input validation, they can't spell either. But the input validation failed, so you can see in the email we've put in basically a SQL injection attack, a far simpler one, password, login. That's gone to our security Lambda function. That's checked with our SQL injection analyzer. It's come back and said that's SQL injection. You really don't want to let that through, and it's failed the authentication. Over to you. Thank you.
Thanks, James. So as you can see, James has got a prototype wrapper working for actually dealing with the front-end data flow into a Lambda function. Now let's take a closer look at the back end. When we were discussing this at the London Enterprise Summit last year, we were thinking, okay, we've got this Lambda function in the middle. We've got our wrapper on the front end. What are we going to do on the back end? Because we want to be able to instrument what's coming out of our Lambda function, maybe log some things using API gateways, logging capability, before things actually go hitting the actual AWS API endpoint. We don't want to have our Lambda function that we are developing and testing, making calls we don't necessarily want it to. So we could use another Lambda function here to actually do some filtering on it. So what can we do here? We can potentially take a look at our API gateway. If you look at API gateway from the right kind of angle, it looks a lot like an actual AWS API endpoint. So it supports SIG-v4, it supports all the usual RESTful vocabulary. How can we actually make our Lambda function talk to an API gateway and think it's actually an API endpoint? Well, depending on which language you choose to use, it's not that hard. So I had a bit of a dig around in Boto and also in the Java SDK, and I came across this file that for each AWS service, this is all essentially the file contains. For each AWS service is a great big JSON structure. It contains a mapping between the different regional endpoint names and their fully qualified domain names. So how about, bearing in mind all these, of course, are rooted in AmazonAWS.com, as are the domain names and TLS keys of API Gateway, how about we just go editing this mapping, and then if we haven't actually got any keys cached from having previously, in our client, from having previously made calls to a real API endpoint, how about we make the SDK under the lid of our Lambda function start thinking that an API endpoint is actually, an API gateway is actually an API endpoint. Now, you would need still to do a bit of modifying on your Lambda function in that you'd need to, first of all, before invoking your real useful doing stuff work, verify that the modified mapping is in place, but otherwise it can be done. I've had a brief look at some of the other SDKs, and I admit I've not quite found an equivalent to this file yet in those, but the mappings are going to be spread throughout the SDK in some other way, in just the, rather than actually just being centralized in a file in the way they are in Boto and the Java SDK. So about a day or so after I figured this out, I thought, hang on a minute, this isn't actually applicable to just serverless stuff. And that I can actually do a useful generalized architecture for this. So if we consider a proxy architecture here, I've used a little head and shoulders and a bounding box to denote an AWS account here, as I haven't actually found a sort of standard symbol for it yet. But if we hack our SDK in our client here, and I've got the file names here of where those actual mapping files are in Boto and the Java SDK, we can then actually set things up so that our API gateway uses SIGV4 and just essentially unpacks our SIGV4 submission. There's a lot of clever things you can do in the API gateway in terms of transcoding RESTful functions, having extra Lambda functions called depending on which REST vocabulary you're using. But in this context, it's probably easier to just go passing a REST call or a query URL onto the Lambda function. So we do that over HTTPS. And then we get to our Lambda function where we can do something interesting, whatever interesting thing we decide to do. There is an extra subtlety here. So our original API call from our client essentially terminates here at our Lambda function, gets inspected and acted upon. And one action that you might expect is for that Lambda function to say, okay, I'm happy with this call. I'm going to pass it through to an API endpoint and cause it to be actioned. But the context of our call actually changes in two ways at this point. In that, first of all, the call that our Lambda function is going to be making is made on the behalf of the Lambda function, not on behalf of the user. So we've got a role here, which our Lambda function has, cross-account into our resource account there on the right. But also, because we're issuing our call cross-account, we've got a completely different ARN involved. We're dealing with a completely different AWS account ID. This makes life interesting. So we go making our call, whatever that may be, and then we have our IAM role giving a cross-account permission to our Lambda function. Note at this point that our resource account doesn't necessarily even know who our client over on the far left is. It can have no sight at all of that user's credentials. This can get really fun. So let's actually have a look at some of the things you can do with this. Now, I like config, and I like config rules. It's great to have a configuration management database for my AWS assets. And also, it's great to have an environment that every time some interesting API action happens, can go look at the state of my AWS environment and say, do I really want this thing to happen or not, given what the disposition of my other assets look like? However, if, let's say, I was to do something that my policy might want me not to, let's say I want to go creating an EBS volume without encrypting it, that might be against my policy. The controls on IAM, which I think of very much as being like Linux-based role-based access control writ large, aren't quite fine-grained enough to be able to do full deep inspection on an API call and say, yes, you can go creating EBS volumes in this region at this time of day, if you've got an MFA token, etc. But it can't make you say, and it must be encrypted. Now, if I go creating an unencrypted EBS volume currently, I could have a config rule that will fire when it sees the creation of that volume, and it will go, that's not fun. Either alert someone, or more constructively, as was shown last year in the Wrangling Security Events in the Cloud session, it can say, I'm going to get rid of that volume, I'm just going to delete it. However, that volume has been created. It has existed for some number of milliseconds before the config rule fired and decided to get rid of it. That might be enough in certain very tightly constrained, highly regulated environments to take you out of compliance. So wouldn't it be useful if for simple non-compliant actions that you don't want people to perform, but are still a bit more fine-grained than IAM can handle, if you were just able to just do deep inspection in your Lambda function on your API call, and if you see something you don't like, say, 401, no way, dude. So I call it preemptive config rules. That's just a nickname more than anything else, but it's a use for this kind of architecture. Next, source IP restrictions. Great thing to have in IAM, very useful. Lots of people use it so that they require their developers to VPN into their corporate environment before they can go making changes to their AWS world. Not every API call these days actually supports this control. If you have an API call which at some point in its execution makes another API call on your behalf, sometimes it won't actually support a source IP restriction, and there's a link there to the details in IAM as to what the limitations are there. Now, if you're actually doing this in a two-stage manner, as we can with our little proxy, you can do your source API filter in your Lambda function, and then in your actual API call, if only your Lambda function and no users have the ability to make the real API call to perform the action, then you don't actually need to have the source IP restriction, because the call is going to be coming from your Lambda function in your role. Normally, I would expect that would be sufficient control in order to enable the call to be honored according to most people's security policies, but I'm happy to be corrected. Please catch me afterwards if so. Third option, and this has, again, events have moved slightly on in that if you want to go encrypting your SQS payloads using KMS, you could actually use KMS's bring your own key function so that you now actually have the original, in fact, of your key at your client end. So you could encrypt your actual SQS payload client side and have the whole thing pass through the system to the far endpoint. But before that happened, so you could potentially do this with some other services, you could actually, if you wanted to encrypt a payload in SQS or some other messaging service where you were passing data through some environment where you needed to have your payload encrypted, you could actually transparently use a Lambda function to encrypt your payload immediately after the API gateway, so that it then proceeds through the whole of the rest of the system until it reaches the appropriate endpoint that has a decrypt grant on the same key to be able to decrypt it. And of course, you just give your Lambda function an encrypt grant. So again, this is something useful that some people may want to do. And this is one that my friend and colleague Bertram Dorn, who has the same job role as me and is based out of Munich, came up with. We've all encountered the kind of software engineer whose idea of performance tuning is to run his code on a C48X large. It'll be a C5, of course, now. So let's say you're a little startup and you might not want to have your engineers launching really big instances all across the board. How about you have a means of interfacing with a workflow system? So if I happen to be the director of engineering in this little company, if a chap comes along and says to me, I need a C48X large, and can give a good reason as to why he does, then I may say, okay, I'm going to put a message into SQS that says, you, Fred, can have a C48X large. At which point, he goes spinning up his C48X large with his regular API call. The Lambda function says, okay, I am going to look on SQS for a message authorizing this action. So that message could be signed, there could be other authentication in it, but SQS, the Lambda function can then consume the message from SQS, thereby obviously deleting it from the queue, and allowing Fred his big box. If, however, Fred wants to run something fairly trivial that doesn't need a box of that size, he tries that again, bzz, 401 again. So lots of people talk about workflow systems. Interfacing them actually into AWS call process is a more interesting proposition. This is kind of the beginnings of a way of doing it. And finally, of course, we get into doing the superset of what James has been talking about for Lambda functions, but for the whole AWS API. So actually doing badness filtering for every single API call, if you want to. Obviously, being British, this made me think of the requirement for anti-malware in the Cyber Essentials program. It would be interesting, hello Tony, to talk to someone about whether this would fit the bill. So regarding what you can actually trigger with Lambda functions, the list is reasonable size and it's getting bigger. So you're only really limited by the ideas and use cases that you come up with as to what you may actually be able to do with this. So just to have some conclusions on this piece, we have another couple of interesting tools for the box. Obviously, IAM is your first port of call for scoping things serverless. API endpoints are pretty well protected themselves, but we can do even further things at layer 7, given what James has been discussing, also filtering and protecting Lambda functions. But we can extend this by actually making an API gateway, pretend to be an API endpoint, and use a Lambda function to do all sorts of other entertaining and useful things. This is just really the beginning of this piece of architecture. I'd love to see in the feedback whether you like these ideas, and if you have any more that you'd like to discuss, then please let's talk about them. We'd love to see some further use cases. Now, bearing in mind I normally run a Mac, I'd like to give you a little bit of a look at something extra that I've been working on recently. From the world I come from, before my AWS days, I did a lot of work for people who, among other things, carry guns for a living. So they were insistent on there being full mandatory access control on their systems so that they could go talking to environments at multiple protective markings from the same client. In terms of mandatory access control, actually, Glacier Vault Lock really is probably the first service in AWS that, first feature, that actually has mandatory access control within a single account. Once you set the lock on a vault policy, not even root can go interfering with it. So how to actually go about reducing the capability of root in an AWS environment. I mean, there are customers who want this. I get this from time to time in my day-to-day work. Obviously, if you're going to get rid of root properly, it's going to take work from IAM engineering. And that particular service team has been doing some very fun work of late with organizations, which launched a couple of days ago. Quite where organizations is going to go over and above the features it's currently launching with. That's not something that I can really talk about that much. I've been looking into it. It does have a really fun roadmap, though. So with multi-factor authentication tokens, you can effectively put root beyond use. In terms of you lock your token in a safe, the idea is then you need access to the safe in order to use the account. But root is still findable. I mean, every AWS account has a root user. So if you have the details of the AWS account, you know there's a root user. That root user is traditional Unix omnipotent. That is still some kind of a target. So could we change this? Could we completely mask an AWS account so that the account ID is not visible? Let's have a look at this some more. Now, my pal Bertram, being German, is rather interested in privacy, and there is actually some interesting privacy law in Germany that requires particular handling of personally identifiable information. He tells me that you can only actually hold PII for a certain period of time, unless you have a particular use for it. So if you're going to be maintaining long-term log archives, which of course we recommend everyone does, then you're going to need to do some filtering and redaction on your logs in order for you to be able to actually hold them long-term legally. So he wrote himself a Lambda function. The idea here is on the left, you've got data coming in from CloudTrail and other log sources. It lands in an S3 bucket the way these things do. Bertram's Lambda function triggers on this event, and obviously things like CloudTrail logs are consistent in terms of JSON structure, so he just finds the relevant bits of PII, stars them out, and then writes that data to another bucket that he uses that is used for long-term archive. The bucket that the logs landed in originally, you just use S3 to set a lifecycle rule on it so that those logs get deleted after 30 days or whatever is considered to be the appropriate maximum retention period for log records that have PII in them without particular reason to. So how about we modify this? Instead of actually redacting PII, how about we redact account IDs in CloudTrail logs, billing records, all this other stuff? So if we now take our proxy model from beforehand and we look at putting a couple of these together, what we get is a big complicated diagram. So let's take this from the inside out. If we take our empty account there, which is essentially our resource account, the idea is that any logs generated in that account go into our billing bucket and our logging bucket, as recommended in our multi-account architecture, and we use the modified version of Bertram's Lambda function to go starring out the account ID, and then putting that data in further buckets outside of our big red oval. We then have our proxy environment, as previously described, just immediately to the left of our resource account, which is able to assign subsets of permissions to other front-end accounts that our client environments actually interact with. So for instance, you could actually split up here into, again, separate API endpoints for every AWS service that people need to interact with. Each of these can have its own filtering on it, but the thing is, not even root in those front-end accounts can change the set of permissions that they are granted by the middle left account on the actual resource account. So the idea here is that outside the red oval, you can have all your actual human users, including people who have the root accounts, and these individuals will have no idea of what the actual account ID of the resource account in our red oval is. Only the 3 other accounts that are inside the red oval have the ability to get information about the account ID of the account that's got the resources in it that's doing the really useful stuff. And you can constrain those very hard in terms of only having really highly trusted individuals being able to have account IDs in those accounts. So this is essentially the same thing in words for people who are going to be using the SlideShare version of this. And again, having spent about 10 years of my life working with old school B1 certified systems, what we've got there in terms of policy being both invisible and immutable to all users, including root, and thereby root privilege being restricted, it's mandatory access control. So that essentially is what we've got for you. Thank you very much for your time. Also,